In this module, we will consider the moment of inertia. We have seen that the moment of inertia of a point object of mass m at the end of a rigid massless rod that allows the object to rotate about a fixed axis is given by m times r squared, where r is the distance of the point mass from the axis of rotation. Now, any object can be considered as a collection of point masses. So we define the moment of inertia of an object as a sum over all the point masses that make up the object, with each mass multiplied by the square of the distance from the rotation axis. Computing the moment of inertia requires that we specify the rotation axis. Consider two equal masses separated by a distance d. If the axis of rotation passes through the center of mass, then we can calculate the moment of inertia through the center of mass as the sum over the two objects. The first one of mass m at a distance of 1/2 d, we square that. We add to that the other mass multiplied by its distance, also 1/2 d squared. The result is 1/2 md squared. What happens if the axis of rotation is moved to pass through one of the masses? Then what we find is that the moment of inertia is going to be the first mass m times its distance from the axis of rotation, which is 0, plus the other mass times its distance, d squared, and the total is md squared. The moments of inertia are different because the masses are distributed differently relative to the axis of rotation. For a continuous distribution of mass, the moment of inertia is defined by transitioning from a sum to an integral, where we integrate over all of the infinitesimal little bits of mass that make up the object, each multiplied by the square of its particular distance from the axis of rotation. So, for example, a solid cylinder of radius r and mass m has a moment of inertia about its center of mass, which is 1/2 mr squared. If we consider a long, thin rod of length L and mass m, the moment of inertia about its center of mass passing perpendicularly through the rod is 1/12 ml squared. And if we consider a rectangular plate of mass m, the moment of inertia through its center of mass is 1/12 m times the sum of the squares of the lengths of the two sides of the rectangle. Now notice that in none of the cases does the dimension of the object parallel to the axis of rotation matter. That is, the thickness of the disk does not matter, nor does the thickness of the plate. And our thin rod, we could make it extend out along the axis of rotation, parallel to the axis of rotation for any length, and it doesn't make any difference towards the moment of inertia. It does contribute to the total mass of the object, but as long as we keep the mass fixed, we can change the dimensions of the object in the direction parallel to the axis of rotation and not change the moment of inertia. It is easy to compute the moment of inertia about a new axis so long as the new axis of rotation is parallel to the original axis. You know the moment of inertia for that particular axis, and you know the position of the center of mass of the object. For example, consider the following object. Let x mark the center of mass of this object of mass m, and let the moment of inertia for rotation about an axis perpendicular to the screen and passing through this particular point marked by x, let it be given by I sub cm. The moment of inertia I for rotation about an axis that is also perpendicular to the screen but passing through a different point, this time labeled by the circle, a point that is a distance d away from the center of mass, it is going to be given by what is called the parallel axis theorem, which says that this moment of inertia is equal to the moment of inertia through the center of mass plus m times the square of this displacement away from the center of mass. For example, consider our solid disk, which has a center of mass moment of inertia of 1/2 mr squared. If we translate the axis of rotation to be along the edge of the disk, then what we find is that the moment of inertia is going to be given by the center of mass moment of inertia plus m times r squared, where r is the distance that the axis of rotation has been translated. We add these together and get 3/2 mr squared.